Hey there, friends. It's been yet again. This is a video for the differential calculus class, and we are looking at the derivatives of trig functions. In doing this, the main thing that we have to have is that limit from a while back that as theta went to 0, sine theta over theta turned into 1. And then from that, we also found out that as theta went to 0, 1 minus cosine theta divided by theta would go to 0, okay? So keep those in mind as we go along here, and we're going to just go ahead and establish our basic trig derivatives, and then from that, we'll see where else we can get. Okay. So your derivatives of trig functions that are going to start out with showing that the derivative of sine is cosine. So we're going to think about this as having f of x be sine of x, so that we can talk about f prime of x just using a definition. And that definition had the limit as delta x went to 0 of the sine of x plus delta x minus sine x, all that over the delta x. Okay, so that was just definition stuff. And I think maybe I'll move that down here. Yeah, okay, because it'll be a little bit easier to follow as we go across instead of down. So what we've got to know is our trig identities here. And I'm going to write out here above, sine of a plus b will be sine of a cosine of b plus the sine of b. And I did not leave enough room. Sine of b times the cosine of a. Okay, you can write that a little bit differently. So if you happen to have memorized it in a different way, it's probably going to be completely fine, but you have to be able to look that up and remember what was going on. Okay, so for our purposes, the a is going to be x and the b is going to be the delta x. So we're going to write sine of x cosine delta x plus the sine of delta x cosine of x, and then minus sine x. All that over the delta x, right? Now, what you have to spot for this is that these two pieces here, and I don't know why it made a curved line, but okay. These two pieces here both have a sine x in them. So we're going to group those together in what we do next. So we will write equals limit delta x is still going to 0. I will factor out a sine x and be left with cosine delta x minus 1 divided by delta x. And then the other piece, I'll have plus sine delta x divided by delta x cosine of x. Okay, now that is a special limit. So special limit, I'll just say special limits because there's the two of them there. And we're going to end up getting the sine x being multiplied by 0 plus 1 times the cosine of x. Yeah. And it's important for us to notice that x was a value. What value was it? We don't know. We need to be able to leave it unspecified. And the delta x was going to 0 no matter what the x was. So the delta x going to 0 did not change the x, and therefore we're able to find this general formula for the derivative of the sine. Okay. All right. So let's do it for the cosine. Now, here's what would be super good for you to do. Pause the video here and try to repeat what we just did without making reference back to what I'm doing, unless you need a hint. Okay, so I'm assuming you've done that and come back. That was a tricky problem, wasn't it? So we say g of x equals our cosine x, and then our g prime of x is the limit as delta x goes to 0, cosine of x plus delta x minus cosine of x, all that divided by delta x. Okay, so if you have unpaused the video to get a hint here, the hint you're probably needing is this: cosine of a plus b is cosine a cosine b minus sine a sine b. Okay, so for our purposes, oh, and if you want to go back and pause, go ahead. But if you're needing further hint, or if you're just confirming that you did stuff right, our a is going to be x and our b is going to be delta x. So we have to say cosine x cosine delta x minus sine x sine delta x minus cosine x. All that divided by delta x. Okay, so then the next sort of hinty bit here is that we're doing the same thing as we did on the previous problem. We've got that cosine x that we're going to get factored out. So limit delta x is going to 0, cosine of x, and then we have cosine delta x minus 1 divided by delta x, and then minus sine x times sine delta x over delta x. As remember that as delta x goes to 0, it doesn't change what x is. And so we have our special limits appearing in this again, and they will give us cosine of x times 0 minus sine of x times 1. So we end up getting that the derivative of cosine is minus sine. Okay, I have a hard time remembering that. All right, let's do another one here. And this one requires us to know some trig identities, but this is trig identities that you may know a little bit better. So we're going to maybe call this h of x equals tan x. And you're probably expecting me to go ahead and do the limit definition again, but I'm not. We are going to be able to establish this one by getting our sine x and cosine x involved. So now this is the quotient rule, and when you work your problems in class, you probably need to have the quotient rule sitting out beside you in the notes. So write that down somewhere, that the derivative of f over g is going to be f prime g minus f g prime over g squared. Okay, so for our purposes, we have to think, what is the derivative of that top? The derivative of sine is cosine, and then times cosine minus, now we have to say, leave the top alone and get sine, and then the derivative of cosine, which is minus sine, and all that divided by cosine squared. Okay, so the negatives go together there, and you have cosine squared x plus sine squared x, all divided by cosine squared x. And from trigonometry, you know that cosine squared plus sine squared, as long as they have the same argument in them. You know, if it said cosine squared x and sine squared y, this wouldn't work. But since they both say cosine squared x and sine squared x, then you have 1 over cosine squared, and 1 over cosine is secant. So we end up with this secant squared of x, okay? Now, to do the derivative of the cotangent, it would be cosine over sine. To do the derivative of secant, you can talk about 1 over cosine and use the quotient rule. So all of the 6 trig functions have derivatives that you can work out with tools that you already have. This is, to me, one of the nicest things about math is the fact that it's built in such a way that you can go get all this stuff figured out yourself. Now, to be fair, most of us would not think to do this stuff. It just, you know, but we can get all the pieces from all the later pieces from the earlier pieces. So, so if you want, you might take and copy those down into notes as formulas that you'll need to have popping up every once in a while. So this is one of those where I'm asking you to show that something is a solution to a differential equation. And it's really just an excuse to make you do some derivatives and some algebra, but it's a skill to talk about it nonetheless. If you want to show that this function is a solution to this, you don't have to solve this. You're already given the solution. So what you have to do is to start with one side and show that it turns out to be the other side. Always start with the complicated side, okay? So we're going to have to first figure out what y double prime is. But to get there, we have to get y prime. So y prime, a is just a constant. Derivative of sine is cosine. B is just a constant. And the derivative of cosine is negative sine. So now we can figure y double prime by just taking the derivative of that. And we'll have minus a times the cosine. Wrote the wrong thing down, Ben. Minus a times the sine, because we're taking the derivative of the cosine, minus b times the derivative of the sine does not pick up an extra minus, okay? So y double prime plus y is equal to minus a sine x minus b. I apologize, folks. And then I apologize for not fixing that right. I wrote down the wrong thing here, and I don't want to go edit this. So, all right. Y double prime plus y is going to be minus a sine x minus b cosine x. Then we have to say plus the original y was a sine x plus b cosine x. And so you can see that you have these things that cancel out together. I guess I should cancel them maybe in red. And that means that you end up with 0 plus 0, which is the 0 that you had over here on the right-hand side. So when you're asked to verify something's a solution to a differential equation, it's purposely meant to be an easy problem. But lots of times people misinterpret it as a hard problem because they think they have to find the solution. No, the solution's already given to you. It's just plug it in, follow the rules of algebra, and so show that the left side is equal to the right side. So, all right. Let's see, number 6, example 6, find the first two derivatives of x cubed sine x, all right? So we're going to have to use a product rule to get there because we have two pieces. So our f prime of x, off to the side if you need it, fg prime equals f prime g plus fg prime. So take the derivative of the first part, 3x squared, leave the second part alone. Plus, now leave the first part alone, take the derivative of the second part. Okay? And that is a perfectly fine way to leave it. You might, in some cases, want to factor out here, like to say, I can see an x squared that comes out of that. So I have 3 sine x plus x cosine x. For what we're doing, that's not really an efficient use of your time. But sometimes if you were like wanting to set this equal to 0 and solve, then you might want to actually do that. Okay. But for our purposes, we're needing to take the derivative of that thing. And you should stop and say, is there anything I can do to simplify this? If there was an x squared sine x and a minus x squared sine x, you'd cancel them out or something. Okay. But for what we've got, we don't have that coming out. So we're going to go ahead and do the f double prime of x. And that means that we're going to have to do each piece here separately. And so I'm going to do the first part, and then I'll come back and remove the underline and stuff. But we'd have 3 times the whole thing, and we need to take the derivative of each piece separately using the product rule. So the derivative of x squared is 2x, and you leave the sine x alone. Plus, now you leave the x squared alone, and the derivative of sine x is cosine x. Okay? Plus, now I'm going to take and think about the x cubed cosine x instead. And so for it, we will, like before, use the product rule. And the derivative of x cubed is 3x squared. Leave the cosine alone. Plus x cubed times the derivative of cosine is minus sine. And now we just have to simplify, okay? So in this case, we'll probably have some terms that go together in order to simplify a little bit. Okay, so you can see that this part here must go together, right? I should have gotten a neater curve with that. So this part here goes together. The rest of it, yeah, I don't know whether you really want to match those up or not, you know, if you want to. So I'll go ahead and put here that I've got 6x sine x minus x cubed sine x. And I'll probably try to factor something out of that. And then plus 6x squared cosine x. So if you want to, you can say that you can factor out an x and a sine x there and have 6 minus x squared and x and then sine x and minus 6x squared cosine x. Okay. I guess you could further see that an x factors out of the whole thing. So if you were asked, for example, to find where the tangent lines were horizontal and you needed to set this all equal to 0, you could factor out and get x equals 0 as one solution. So, all right. So let's tackle this one here. And now we're going to have to find the first two derivatives of cosine x over sine x. So like before, we're going to have to use the quotient rule. I already referred to that to y'all, so you should have that noted down. Derivative of the top, derivative of cosine is minus sine. And then we have a copy of the bottom that we leave alone, minus. Now we'll leave the cosine alone and have a derivative of the bottom, which is just 1. And divide all that by, divide all that by the square of the bottom, so x squared. And so you're going to have, I'm going to pull a minus out to the front and have x sine x plus cosine x all over x squared, okay? The reason I pulled the minus out to the front is that we're going to have to take a derivative again, and we can just leave that minus hanging on as just a factor. All right. Then g double prime of x, we're going to have to go back and remember our quotient rule again, and it says to take the derivative of the top. So the top there, you got this x sine x and this cosine x. So this is getting pretty complicated. So the derivative of x sine x, you'll have to use a product rule for, and you get a 1 sine x plus x times the derivative of sine, which is cosine, okay? And then plus, we'll have to take the derivative of cosine, which is minus sine, okay? And then times the x squared from the bottom. And then minus, now we have to have a copy of that original top there, x sine x plus cosine x times a derivative of the bottom, which is going to be 2x, all of that big mess, divided by the square of the bottom. Well, the bottom was already x squared, so x squared squared is x to the 4th, okay? All right, so let's see what we can do to simplify it. I think y'all have already spotted that this sine x and this sine x will cancel out. Other than that, I'm not spotting anything just yet, but I'm going to keep my minus sitting out to the front. And so that, and I will have x cosine x times the x squared. So it's really x cubed cosine x. Make sure you don't try to suck the x or the x squared into the cosine there. That's just a common copying mistake for people to make. But then minus the 2x times the x sine x, so 2x cubed sine x. I said cubed and I was just lying to you. I meant for that to be 2x squared sine x. I was testing you, that's what it was. Okay, minus 2x times the cosine x. All that divided by our x to the 4th. Okay, now one little bit further about simplifying. Y'all should be able to see that there's an x that is a factor of the whole thing. And since I've got more minuses in there, I'm going to try distributing that minus back through and have minus, now let's hang on. I'm going to have x factored out and have minus x squared cosine x, and then plus 2x sine x, and then a plus 2 cosine x, all over my x to the 4th, which I will then do a little bit of cancellation with in order to make it a little nicer. And I don't know, I guess I'm going to write this minus x squared cosine x plus 2x sine x plus 2 cosine x all over x cubed. Now, if you wanted to, you could have grouped the cosines together and had a 2 minus x squared cosine x. But yeah, that's about as nice as you could make it there. Okay. All right, let's call that good and take a look at this one here. This asks us to find a tangent line at the point 0, 1. So as y'all recall, to find a tangent line, you first take the derivative of the function, and then you'll plug in the point that you're interested in. So our derivative of the function, oh no, we have to use the product rule yet again, and that's kind of an ongoing theme. So we take the derivative of the first, and the derivative of e to the x is just e to the x. Leave the second alone, plus leave the first alone, take the derivative of the second. Okay. And so you might spot there that you could factor out an e to the x and have this cosine x minus sine x. That doesn't really make it any simpler, but if somebody were asking us now to take the second derivative, we would be totally prepared to do that, right? So we want the h prime of x, oh, I'm sorry, the h prime not of x, but at 0, because we get the point 0, 1 that we're plugging in. So e to the 0 cosine of 0 minus sine of 0. We should all know that e to the 0 is 1, cosine of 0 is 1, sine of 0 is 0. So you end up with a 1 there. So using the point slope equation of a line, y minus y naught equals m times x minus x naught. And if you want to, you can go ahead and solve and get y equals x plus 1 as your equation there. Okay, yay. All right. So then this one's going to ask us to find the intervals where p of x equals x plus 2 cosine x is increasing or decreasing. And I'm going to, instead of looking in 0 to 2 pi, I'm going to say, let's look minus 2 pi to 2 pi, okay? Just because if you take a look at a graph of it and you just look at 0 to 2 pi, it doesn't really show you much of what's going on. But once you get 2 periods of the function, you really start to see what's happening with it. So, all right. So I'm going to go ahead here and say p prime of x is going to be equal to just 1 plus 2 times the derivative of cosine is minus, minus sine. And so that's going to be 1 minus 2 sine x. We have to set that equal to 0, which says that the sine x needs to be equal to 1/2. Okay, so now we're going to have to think about our unit circle. Our unit circle. And so I'm drawing a real quick picture of a unit circle here that I hope is helpful. And sorry, I'm a little bit OCD about getting those things just so. All right, so here's our unit circle. And the thing we have to think about is we have a positive value for sines, and sines are going to be something that is happening or that is placing something horizontal, okay? So you will then think about getting a, getting a reference angle here. Reference angles are always positive and acute. And so I'm going to say something about the reference angle being equal to, it's a special angle. If it wasn't a special angle, you'd whip out your calculator and get an approximation just by doing inverse sine. But you ought to have this one memorized as pi over 6. Okay. Now, once you have that in mind, then the other angle that we've got here that you can see in the picture is going to be a supplement to that angle. And so we're going to start producing our x values and thinking about those are kind of the breakovers, right? So x equals pi over 6 and pi minus pi over 6, because you had to back up from the 180 like that, which is 5 pi over 6, okay? Now, to figure out where to test things in, I'm going to make kind of a long line there and put minus 2 pi down here and 0 here and 2 pi here, okay? So we know that we need to have something at pi over 6 and something here at 5 pi over 6. And so what makes sense to do is to just think about subtracting 2 pi on each one of those. So 1/6 minus 2 pi over 6 minus 2 pi is going to end up being minus 11 pi over 6. And 5 pi over 6 minus 2 pi is going to be minus 7 pi over 6. Okay. So for places to test, 2 pi is a super convenient value. And so in here between minus 11 pi over 6 and minus 7 pi over 6, I think we end up with minus 3 pi over 2, okay? And I should maybe, sorry. I'm going to take these pieces out of the way here that were not actually critical values up above, okay? So then we can test 0 in there because it's not one of our critical values. And then we can test pi over 2, and then we can test 2 pi, okay? Now, if you're saying, oh my God, that's a lot of points. Yes, but they're really quick to plug in, okay? So p prime of 2 pi, we're saying 1 minus 2 times the sine of 2 pi is 0. Then p of, I said 2 pi, I meant minus 2 pi, sorry. P of minus 3 pi over 2 is 1 minus 2 times, okay, minus 3 pi over 2. So it's going to turn out to, sorry, my brain is missing this real quick. The sine of 3 pi over 2 would be negative 1, but because this is negative 3 pi over 2, you get a positive 1. So we end up with a negative 1 out of that. And then p of 0 is 1 minus 2 times 0, which is a positive 1. P of positive 3 pi over 2 is 1 minus 2 times, I said 3 pi over 2, and I meant 1 pi over 2. So, yeah, you end up getting negative 1 out of that. And then the last place to test is p of 2 pi. And that's going to be the same thing as we've seen before. and we get a positive 1. So increasing, decreasing. So for the increasing ones, you will pick out the intervals where it's positive. Now remember, at the ends of the interval, you can actually go ahead and include those. So minus 2 pi up to, what was the first critical value? Minus 11 pi over 6. And then we have an open, and then we don't include the stuff that's going from minus 11 pi over 6 up to 7 pi over 6, but then we go minus 7 pi over 6. And then up to the next critical point was pi over 6. Okay, and then the last bit there starts at 5 pi over 6 and goes all the way to 2 pi. Okay. Then for the decreasing, that's going to be the ones that were negative. And so those are these test points. They happened here and here. And so we can say that we wanted to go from minus 11 pi over 6 to minus 7 pi over 6. And then again from pi over 6 to 5 pi over 6. Okay. And that gets us our intervals there. So, all right, I think I've got one more here. So, okay, yeah. So this one, we're going to determine where the function is concave up and concave down. So we're going to have to get q prime of x in order to get to the q double prime. So you have to, we don't have the chain rule yet, do we? Oh, that changes how I was going to write this out. So let me change this in order to write q of x equals sine x, sine x, sine x. Okay, so here's a trick. If you have to use a product that has 3 things in it, you go through and take the derivative one at a time. Now, we can actually show that by taking an f times g times h and expanding out all of the stuff, but I'm just going to state it because it is going to take extra time to explain the exact reasoning. Okay, so the thing to notice here is that we just went through, and on each thing that you're adding up, you're going to have one thing having its derivative. They just go through and take turns. Okay, so when I say something about having this this q prime of x here, then I can say, well, that is cosine x times sine x plus sine x cosine x sine x plus sine x sine x cosine x. So if you'd like to simplify that, then you could just say it is cosine x times sine squared x. Okay. Then when we do the q double prime of x, it's going to be helpful to think about it as the 3 products again. And so if we're going to think in those terms, then I'll put it like that. We have to take the derivative of the cosine is minus sine x, and then the other 2 are left alone, plus, now we leave the cosine alone, and the derivative of the sine, the first sine is a cosine x, leave the second one alone, plus, leave the cosine alone and the first sine alone, the derivative of the last sine is a cosine. And now we want to simplify as best we can. We'll see minus sine cubed x and then plus 2 cosine squared x sine x. Okay. So since we're going to have to actually do something with this, we'll want to see what we can factor on it. And I can see that we can factor out a sine x, and then we're left with 2 cosine squared x minus sine squared x. I'll bet that that simplifies in a nice way. Let's try turning sine squared into 1 minus cosine squared. So we still have the sine x, 2 cosine squared x minus this 1 minus cosine squared x. So that's going to be sine x, and notice that we have minus a negative here. So we end up with a 3 cosine squared x minus 1. All right. So that took up a lot of the page here. I'm going to have to go ahead and insert an extra page. And remember, we've got sine x. I will just come back and copy it. So copy, paste, and I'll put, what was it? H, Q, Q. So, and I can't write a Q. Q double prime of x, and it's equal to this, and we needed to set that equal to 0 and solve. Now you'll see why it was such a good idea to factor, because once you have it factored, then you can set each factor to 0 and see what that gets you. And the sine x equal to 0 is going to get you that, that the x for that had to be a multiple of pi. So 0, pi, or 2 pi are our possibilities. I think it said we were going to look at it in 0 to 2 pi, didn't it? Yeah, in 0 to 2 pi. Now, this other one here, though, is less nice. You end up having cosine x is equal to either plus or minus 1 over the square root of 3. 1 over the square root of 3. That's not a special angle, right? So what we will end up needing to do is to actually think about our unit circle stuff again. But for our unit circle, we are going to have to be aware that the angle we talk about is going to be something that's not special, okay? I'm going to flip back to the previous page where we had the unit circle crop up. Where was that? Here, right? So I'm going to just copy that and pop back over to what we're working on. And is it here? No, sorry. We're looking at this here. Okay. So I'm going to paste that and maybe make it a little bit bigger so that we can spot where we're going. All right, so we're going to have to think about this slightly differently because of the fact that we're talking about a cosine. So our cosine x, we're going to first of all worry about being positive, right? So I'll put a vertical line here-ish, and we're going to say cosine x equals positive 1 over the square root of 3. Okay. And so then we will know that there's two angles that will be an answer to this, but we will start with cosine of r equaling 1 over the root 3, and having the r be equal to the inverse cosine of 1 over root 3. I happen to have a calculator beside me today, and check to make sure it's in radians mode. And inverse cosine 1 divided by square root of 3 is about 0.955. Okay, actually 9553. When you're doing these, don't round to just 2 digits, okay? All right, so that value there, and then the other value that we would have would go down, and I did not mean for it to do that. The other value here would not be in the first quadrant, but that would be the only thing that the inverse cosine would give you. So the other value that we're going to think about there is going to be x equals 2 pi minus that inverse cosine of 1 over root 3. Okay, so that's the two values that we'll think about from that. And if we wanted to get an approximation on that, that would be about 5.3279. Okay. All right. Then we're going to think about flipping it over and doing the other bit here. I think I can actually get that to work. Yay, I got to flip over just about right. The only thing is that my angle that I'm trying to grab here is just sitting in the wrong place. Okay, and for some strange reason, there we go. All right. So for this, we're actually going to be able to reuse some of our work there. We're still going to have the same reference angle, but now we're going to get our x values to be pi minus this inverse cosine of 1 over root 3. And let's see, that's about 2.1863. And then pi plus the inverse cosine 1 over root 3. And that's about 4.0969. Okay. And you can be much more exact or much less exact as you care to. We're just going to have to look at the various places on the interval to break up and where we have to actually test at. Okay, so we actually have 0, pi, and 2 pi from the first piece there. And then we have these other values, goodness, that I'm going to just put roughly here and here, and the 0.955, the 2.186, and then here and here, we're going to have to plug in, or we're going to have these 4.097-ish and 5.328-ish. Okay, so we need some test values. And, you know, in here, a good test value would be maybe 0.5. If you're saying, oh my gosh, that's not a special angle, you're correct. But the thing that we're going to want to do is to plug this into a calculator and just let it do things for us. Okay. So just plugging these values in is going to let us figure out stuff. And I am going to have to do something real quick with my calculator here and tell it, then I'm going to store the value of 0.5 into a variable, and then I'm going to have to take the sign of that variable and times 3 cosine of that variable squared minus 1. All right. So I am just going to make a quick note here along the side about the Q double prime. And I'm going to go down through here, and we end up getting a positive number here when we plug in the 0.5. What we get is positive 0.628 something. And then we end up getting a negative when we plug in here. Oh, so, pardon. Wow. I'm sorry, folks. I'm just having a hard time getting things stored in the right place in order to get this. So I'm ending up getting a positive 0.273, 0.274, something like that with this one, and then a negative with this one, a positive, and a negative. They don't always have that sort of alternation like that, but it turned out in this case. So for the increasing ones, we want to talk about just where it's positive. And so we will start at 0 and go up to the 0.955. And then we will start again at the 2.186 and go up to pi. And then we will start again at the 4.097 and go up to the 5.328. And then the rest of it is negative. So I'm going to take and push that off to the side here as much as I can so I have the room to write the other piece. All right, so decreasing. So that starts at the 0.955 and goes up to the 2.186. And then it stops being decreasing and it starts again at pi and it continues to the 4.097 and then stops decreasing and increasing. It starts again at 5.328 and goes to 2 pi. And I should have had round brackets all along in these, and I had square ones, but I will fix that real quick. All right, so yay, we have done examples of increasing, decreasing, concave up, concave down. Damn it, that's what sorry, I forgot my terminology. Concave up, concave down. All right, so we've done examples of concave up, concave down, increasing, decreasing. We've had some product rules, we've had sines, cosines, tangents, everything. So this should give you plenty of examples, and I apologize if the video ran on too long. So see you in class.